In the last couple of topics, we've talked about dissolution reactions, how we can dissolve chemicals in water, be they ionic or covalent. In this topic, we're kind of going to look at the opposite process. We're going to look at how cations and anions in particular might come together and fall out of solution. Throughout our conversations here, you remember this, your table of common cations and anions might be handy, might help you keep track of concepts from time to time. Just answer a few questions you might have popping to the surface. So, good idea to keep it handy, although we're not explicitly going to harp on about it. So, as I alluded to before, precipitation reactions is almost the opposite of dissolution. You remember in the last topic we discussed hydration forces and the fact that if you have an ion in water, water molecules might surround it with one end of the polar molecule being attracted to that charged ion. Now, obviously there is going to be an attraction between a positively charged cation and a negatively charged anion, so you might think that they would want to snap back together and form a compound again. In some cases, the hydration, the water surrounding it, is strong enough to hold those ions in place and keep them in solution. That's how we keep them dissolved. But there are many cases where those hydration forces, that water, is not strong enough to prevent that attraction between cation and anion. So if that force isn't strong enough, those two ions will still be attracted to one another. So if you mix those two together in solution, cation and anion will be attracted and they will snap together and form a solid compound. We call this precipitation. That solid compound that we form is a precipitate. If we have a look at an example of that, here I can see the formation of a lead iodide precipitate in solution. So as you can see, it's a quite obvious observation. I've got the formation of a murky yellow brown coloured precipitate there. Chemists find this kind of observation, this kind of interaction really useful. We can use it to separate one chemical from another. We can use it to remove a pollutant from a water sample. Take the case we've got right here. Lead is a particularly nasty chemical. It's quite toxic, known as one of the heavy metals. One way of removing a large amount of it from water would be to add a chemical to precipitate it out. Add some anion, which has a very strong attraction for that lead. There are pros and cons to that technique, but nonetheless it is a method. We can also use precipitation reactions to learn about what chemicals may or may not be present. So we could add an anion that we know might precipitate with lead. If we see this wispy yellow-brown precipitate, we know we've got it. If nothing happens, we know there's probably no lead, or certainly not much there. We could even collect the precipitate afterwards, the solid material that forms, and use that to quantify, to determine the amount of a substance that we have in solution. So precipitation reactions can be very useful for us. So if waters of hydration can sometimes keep these ions in solution and sometimes not, how do we decide? How do we know which ones will remain happily dissolved together and which ones won't? For that, we need to use a solubility table. I have one here for you on screen. This is another one of those things that, yes, chemists will over their careers eventually learn these rules for, but it's certainly not what I have in mind for you. I want you to be able to navigate your way around this table, and we're going to use it to make some decisions. Let's have a look at this solubility table and how it works. So I've tried to color code it for you. So the areas highlighted in green are highlighting examples of materials that will dissolve in solution. We call these materials soluble. They will dissolve in water. The areas I've highlighted in red demonstrate areas where we're showing ions that are insoluble in water. This means that they won't dissolve. They will snap together with another ion and they will form a precipitate. So looking at the top half of the table, this area I'm highlighting, these list the ions that are generally soluble in solution in water. They like to stay dissolved. So for example, you can see all of the alkali metals, remember, all of those group 1 metals, they will all remain dissolved in water. If you then look at the other side of the table, it lists the exceptions there. And you can see there are no exceptions. So any group 1 metal ion, potassium ions or sodium ions, any other one from group 1 on your periodic table, they will remain in solution and there's no other ion you can add from this list that will cause them to precipitate out. Very happy there. If I look at a different area, one which has some exceptions, take this third area here, chlorides, bromides and iodides. These are also normally soluble. They will happily remain in water. The only thing that will cause them to come out and to form a precipitate is if you add silver ions, mercury ions or lead ions. They are the 3 exceptions to that rule. So if you were to add silver, mercury or lead to a solution containing chloride ions, hydration forces would not be strong enough to keep them apart. So that silver, mercury or lead would snap together with that chloride and would fall out as a precipitate. You'd see a solid forming in the solution. If you have a look at the bottom half of the table down here, this works in the exact opposite fashion. On the left-hand side, all of these ions are generally insoluble in solution. If you mix them with most ions, they won't stay in solution. They will form a precipitate. They will fall out as a solid. Over here, we have the exceptions to that. We have the cases where, no, they're actually fine with these few exceptions. For example, if I was to look at carbonate, carbonates generally don't dissolve in water. However, you can dissolve them in water if you combine them with just an alkali metal. If they are the only types of cation present, then they would dissolve. Then they would be fine. Right, this solubility table is going to be much better explained if we have a look at a couple of examples. So what we're going to do is we're going to look at a couple of questions, use our solubility table to make some predictions about it. We'll then cut to the lab, have a look at what's going on, and decide how our prediction went, whether we got things right or missed anything. Let's start by having a look at a reaction between potassium chloride and sodium hydroxide. So here's the start of my chemical reaction, potassium chloride and sodium hydroxide. I've got my potassium chloride waiting in my test tube, ready to go. Before we add though, let's have a look at our solubility table and think about what we might expect to happen. If I have a look at my two compounds, first the potassium chloride. It's made of potassium ions and chloride ions. Have a look at your solubility table. Are there any rules for these? Potassium, up here at the top, potassium is always soluble. There are no exceptions. So potassium is not going to form any precipitate. What about my chloride ions? Chloride, they're up here as well, always soluble unless I'm mixing them with silver, mercury or lead. Haven't got any silver, mercury or lead down here, so chloride's not going to form any precipitate. At this point, if neither of those chemicals are going to do anything, we can be pretty confident that not much is going to happen, but let's be thorough. Let's quickly check the other half. Sodium ions, again, come up the top. They are one of those alkali metals, always soluble, will never form a precipitate. Looking at the other half, hydroxide ions, we find them right down the bottom here. Hydroxides are often insoluble. They form a lot of precipitates. But look over here, your exception is any of those alkali metals. So it's actually fine with sodium, sodium's an alkali metal, and it's fine with potassium, potassium's an alkali metal. So all of these ions are soluble together. They shouldn't have a problem with one another. If we then go into the lab and try this for ourselves, you can see that I've got my potassium chloride solution in the test tube. We're adding a few drops of sodium hydroxide to that. And as we do, you can see that there's no real change in that test tube. There is no reaction taking place. All of the ions are remaining soluble in there together, just like we expected they would. So you can see from our time in the lab that when you mix potassium chloride with sodium hydroxide, that there is no reaction between the two. I'm now going to look at another reaction with you, and we're just going to swap one thing. I'm going to change this potassium ion for a different ion. I'm going to change it for cobalt. So now I'm going to react cobalt chloride solution with that same sodium hydroxide solution. So once again, starting here with just my cobalt chloride solution, it's a nice reddy pink color. Let's have a look at our solubility table and see what we think will change. Now, first of all, the cobalt. You can scan around your table. There are no rules for cobalt on this table, so it will largely do what it's told, depending on what other ions are present. We've already looked at chloride. We know that chloride is fine in solution, unless we mix it with silver, mercury or lead. No problems there. We've looked at sodium. We know that that's always soluble and never forms any precipitates. But let's look at that last ion, the hydroxide again. They are normally insoluble. They love to form precipitates. Exceptions are alkali metals and barium. So sodium ions, alkali metals, are fine with hydroxide ions, but that's not the only cation we have there. Now we've introduced these cobalt ions as well. Cobalt is not an exception. So when we mix cobalt ions and hydroxide ions in the same place, they should snap together. They are insoluble. They should form a precipitate. We go into the lab. You can see here I've got my cobalt solution. We're now adding just a few drops of sodium hydroxide, and as soon as it hits the surface, you can see the formation of a bright blue solid inside that pink solution. That blue solid you can see, that is a precipitate forming when the cobalt ions and the hydroxide ions snap together. Water cannot hold them apart, the attraction is too strong. Looking back at our chemical reaction, Again, we can show this precipitation reaction by putting together the cobalt ions and the hydroxide ions. You'll notice I've got 1 cobalt ion and 2 hydroxide ions in my product. If you remember our discussions on ionic compounds, you'll know that's because cobalt has a charge of +2, hydroxide has a charge of -1, and so to make a real material, the overall charge has to be 0, has to be neutral. So that's why I've built the compound this way. To emphasize it to precipitate, I've noted that it's a solid now, it's no longer in solution. And then meanwhile, the sodium ions and chloride ions that haven't reacted stay left behind in solution. As a finishing touch, of course, I have balanced my chemical equation to make sure we haven't broken the laws of the universe, that we have the same number of atoms going in as we have going out. So that's a look at precipitation reactions and how they behave. In the next topic, we're going to discuss the supremely important part of not just chemistry, but all of the sciences. We're going to talk acid-base chemistry.